Okay, let us continue the second part of today's course. Okay, in the first part of today's course, we have talked about undergo. Okay, let us see what is undergo. Okay, to experience something that is unpleasant or something that involves a change. Okay, so let us go back to the slides. Okay, to undergo slow fading. Conversely, if the channel changes rapidly compared to the signal, the channel is said to undergo fast fading. Since the rate that a channel changes is measured in terms of the reciprocal of its coherence time, and the rate that a signal changes is equivalent to its baud rate, okay, that is 1 over Ts. Okay, do you remember what is Ts? Okay, let us review it. Okay, Ts is the symbol duration. Okay, let us go back to page 180. Let me see. Not 80. Okay, 92. Okay, so Ts is the symbol duration. It follows from the definition that slow fading implies 1 over Tc. Okay, where Tc is the coherence time, is smaller than 1 over Ts. Okay. Furthermore, since the bandwidth of a signal W is approximately 1 over Ts, okay, it is a well-known fact in communications, and the Doppler bandwidth is proportional to 1 over Tc. Slow fading is also equivalent to saying that Bd is smaller than W. Okay, because the Doppler bandwidth is proportional to 1 over Tc, okay, so we can replace 1 over Tc by Bd, and W is approximately 1 over Ts. Okay, so we can replace 1 over Ts by W. So this equation becomes Bd is smaller than W, okay, which is this equation. Table 4.3 summarizes the definitions of slow and fast fading in terms of the intrinsic parameters of a fading channel. Okay, let us go to table 4.3. Okay, table 4.3 lists the definition of slow and fast fading. When the channel type is slow fading, the definition is Ts is smaller than Tc. Okay, that is symbol rate is smaller than the coherence bandwidth, and Bd is smaller than W. Okay, that is the Doppler frequency or Doppler spread is smaller than the signal bandwidth. Okay, when channel type is fast fading, conversely, the definition is Ts is greater than Tc and Bd is greater than W. Okay, next let us go to section 4.6. We will talk about statistics of small-scale fading. Okay, in this section we consider the statistics of small-scale fading in a flat fading environment. we show that small-scale fading often exhibits Rayleigh or Rician behavior. In this section, we define what this means and why the fading often exhibits these statistics. Okay, so first let us look at section 4.6.1, Rayleigh fading. Okay, Rayleigh fading often occurs in multi-path environments where there is no direct path between the transmitter and the receiver. By Rayleigh fading, we mean that the magnitude of the channel response, okay, that is, the absolute value of h of k, is a Rayleigh random variable. As we will see, this fact follows naturally from the mathematical definition of h of k. Okay, to see this, recall that for flat fading, h of k is equal to capital C of tk, f is equal to 0. See discussion leading up to. Okay, what is the meaning of leading up to? Okay, let us see the handout. Excuse me. Okay, page 199, problem 1. What is leading up to? Okay, solution: if a period of time or series of events leads up to an event or activity, it happens until that event or activity begins. Okay, let us go back to the slides. Okay, see discussion leading up to equation 4.41. Okay, let us see equation 4.41. Okay, this equation. Okay, and in the previous page, on page 167, h of k is defined as capital C of tk 0, okay, which is the channel response at that time, that is the time tk, and capital C is the frequency response of the channel. Okay, let us go back to page, okay, here. Furthermore, equations 4.24. Okay, let us see equation 4.24. Okay, we can see that in equation 4.24, okay, the equation number is in the wrong place. Let me correct it. Okay, capital C of Tf is defined as the integral from negative infinity to infinity, small c of t tau times exponential negative j2 pi f tau d tau. Okay, where c of t tau is the impulse response function of the channel. Okay, let us go back to the slide. Okay, 100, page 199. Okay, and equation 4.13. Okay, let us see equation 4.13. Okay, this is equation 4.13. Okay, the impulse response function must have the following form. C of t tau is equal to summation I, where I denotes the ith path. Alpha I of t. Okay, what is alpha I of t? Let us see the definition of alpha I of t. Okay, alpha I of t is the gain of the ith path at time t. Okay, and times exponential negative j2 pi fc times tau I of t, where fc is the carrier frequency. And what is tau I of t? Okay, let us review the definition. Okay, of tau I of t. It is the delay of the ith path at time t. Okay. Okay, and times delta of tau minus tau I of t. Okay, the equation number is in the wrong place. Let me correct it. Okay. So let us go back to page 199. Oops, 199. Okay, here. Okay, show that capital C of tk f is equal to 0 is equal to the integral from negative infinity to infinity small c of tk tau d tau. Okay, why do we have this equation? Okay, this equation comes from equation 4.24. Okay, so let us write this equation. Okay, on the blackboard. Okay, because I do not have a blackboard, so I use the Microsoft Word instead. Okay, so this equation. Okay, then we let t be equal to tk. Oh, sorry. Okay, and f is equal to 0. Then, okay, this equation becomes c of tk, and f is equal to 0. Okay, and this is equal to the integral from negative infinity to infinity small c of tk. Okay, t should be changed to tk, and the tau, okay, and exponential negative j2 pi f tau. Okay, and now f is equal to 0. Okay, so this is equal to the exponential 0. Okay, which is equal to 1. So 1 can be deleted. Okay, so we have this equation. Okay, so you can see that. Okay, back to page 199. Okay, so you can see that capital C of tk, okay, f is equal to 0. Okay, is equal to the integral. Okay, let me turn off the subtitle. Okay, okay, so it's equal to the integral from negative infinity to infinity small c of tk tau d tau. Okay, and that c of tk tau is equal to summation I alpha of tk times exponential negative j2 pi fc tau I of tk times delta of tau minus tau I of tk. Okay, so this equation comes from equation 4.13. Okay, let us go to equation 4.13. Okay, and let me copy this equation. Okay, and times here, paste here. Okay, let me draw a horizontal line. Okay, good. Okay, so this equation. Okay, now we let t is equal to tk. Okay, then this equation. Okay, so we just need to replace each t by tk. Okay, so this t replaced by tk, this by tk, and this by tk, and this by tk. So there are totally 1, 2, 3, 4. Okay, 4 tk here. So let us go back to the slides. Excuse me. And return to page 199. Okay, so we can see that here are 1, 2, 3, 4 tk here. Okay, respectively. So it follows that h of k is equal to capital C tk f is equal to 0. And let me substitute this equation into this equation. Okay, then we have it is equal to the integral from the negative infinity to infinity summation I and alpha I of tk times exponential minus negative j2 pi fc tau I of tk times delta of tau minus tau I of tk d tau. Okay, and then we interchange the order of the summation and the integral. Okay, we get this equation. Okay, and this equation is equal to this equation. Okay, how can we derive this equation from this equation? Okay, again, let us copy this equation. Okay, so I think I need to save this first. Okay, it is chapter 4, page 199. Okay, so save to Blackboard in the memo. Okay, yes, memo. Huh? What's the matter? Okay, so forget it. Okay, so let me close it. Okay, and let me temporarily save it to the desktop. Okay, and this is okay, good. So let me open a new Microsoft Word document. Okay, and this equation. Okay, you can see that because alpha I of tk times exponential negative j2 pi fc tau I of tk does not depend on tau. Okay, so we can move this term out of the integral. Okay, so this equation is equal to move this term out of the integral, like this. And according to the definition of the delta function, this integral is equal to 1. Okay, so we can write it is equal to the summation. Okay, let me copy this. Okay, summation and this is equal to 1. Okay, good. So we can delete this 1. Okay, and we will have this equation. Okay, let me align at the equality sign. Oh, okay. Let me input an equality sign and make this white. Okay, like this. Okay, good. So we can get this equation just like the slides show. Okay, and this equation can be split into two terms. Okay, first term is equal to summation I alpha I of tk cosine 2 pi f c tau I of tk, and the second term is minus j times the summation I alpha I of tk sine 2 pi f c tau I of tk. Okay, it is because exponential negative j theta is equal to cosine theta minus j sine theta. Okay, denoting the first bracketed term by x. Okay, so this term is x, and the second by y. Okay, so this term is y. Okay, we can write the absolute value of h of k as, okay, because now h of k is equal to x minus jy. Okay, so the absolute value of h of k is equal to the square root of the square of the real part of h of k plus the square of the imaginary part of h of k. So it is equal to the square root of x squared plus y squared. Okay, and this equation number is in the wrong place. Okay, let me correct it. Okay. Okay, next page. If we can show that x and y are IID, okay, what is IID? Let us look at the handout. Okay, page 202, problem 1. What is IID? Okay, solution. IID means independent and identically distributed. Okay, let us go back to the slides. Okay, if we can show that x and y are IID zero mean Gaussian random variables with equal variances sigma square, then by definition, the absolute value of h of k is a Rayleigh random variable with a probability density function PDF. F of the absolute value of h of x, h of k of x given by, okay, f of the absolute value of h of k of x is equal to x over sigma squared times exponential negative x squared over 2 sigma squared if x is greater than or equal to 0, and f of the absolute value of h of k of x is equal to 0 otherwise. Okay, so this equation number is in the wrong place. Let me correct it. Okay. Okay, good. Okay, so next page. To show that x and y are IID zero mean Gaussian random variables, we first note from the fourth equality in equation 4.56. Okay, let us look at the equation 4.56. Okay, this equation. Okay, it is 25 minutes. Let us take a break.